The objective of this video is to review the Phasor representation of sinusoidal waveforms. At this point in your studies, you've made extensive use of Phasor analysis to solve steady-state circuits. In this class, we will be using phasors to analyze many periodic quantities. This includes the current linkage of our windings, which is a quantity that is distributed in space rather than in time. It also includes the voltages induced in coils of our windings and the terminal properties of our electric equivalent circuits. So with all this said, I want you to use this video to refresh yourself on the fundamentals of phasor analysis. And we're going to start by going back to the very beginning, the very basics of what phasor analysis is and where it comes from. And phasor analysis is all based on Euler's formula, which says that an exponential can be expressed as the sum of a cosine and an imaginary sine term. And so we can rewrite this expression to recognize the following. And phasor analysis takes advantage of the properties of exponential functions. Specifically, it takes advantage of the property that when you sum your exponents, you can split them out as two functions that are multiplied by each other. And as you're familiar, this first term right here is called our phasor, which we represent as A bar. And so this whole quantity over here, we can use it to represent a cosine by saying that the real value, the real portion of A bar times e to the j omega t is equal to our cosine term. Notice that we've written this in terms of omega t, so it's a transient expression, but you can do the same thing in terms of angular expressions. Where theta goes from 0 to 2 pi. For example, it might be your rotor's location in the air gap as it rotates over a revolution. And phasors we can express either as a e to the j phi, as we've done over here, or we can equivalently write this in a polar form. So the phasor always has a magnitude and a phase angle. Now, why would we want to do this? Why would we want to take this cosine function and express it as a complex quantity? It turns out that phasors are a useful tool for adding periodic signals that occur at the same frequency. And to illustrate this, let's consider this example where we're trying to add three cosinusoids that have magnitudes of b hat, c hat, d hat, and phase angles of phi b, phi c, and phi d. Notice that all these cosinusoids are at the same frequency, which is omega. We can express this in terms of complex quantities to get to our phasor representation as follows, where we now recognize that we have three phasors in here for each cosinusoid. And this quantity right here now becomes our final phasor for our complete system, so that we can write that A of t is equal to the real part of A bar times e to the j omega t. And so we get this final cosine expression. We started off with these three cosines and we added them to get a final expression in terms of one cosine that has a magnitude and a phase angle. And so the complexity here, the math that we actually have to do, is to determine what the value of this phasor A bar is, what its magnitude and what its peak is. And we can take two paths to calculate this. The first is a mathematical approach where we directly compute the quantities of phi and a hat. And the second is a graphical approach where we use what's called a phasor diagram and take the sum of the phasors graphically. And so in this case, we use the Euler formula that e to the j phi is equal to cosine of phi plus j sine of phi. And we can represent this expression graphically using a right triangle. And it's nice to do this because this means something physically to us. We're used to solving the sides and lengths of a right-handed triangle by using trigonometric expressions. So we're used to seeing the magnitude of a triangle and having a certain angle off of the horizontal, and then using that to calculate the vertical rise as the magnitude times the sine of the angle. This is something that we intuitively understand just from seeing it. All right, now let's go back to our expression up here, where each of these phasors has a certain magnitude and a certain phase angle. And let's employ this expression to write this out in terms of cosines and sines. So I've grouped these terms in terms of the real components and the imaginary components. And I've done this because we're going to be using these real and imaginary components to calculate the magnitude and the angle of our phasor A, as follows. So we've now solved this problem. It was a little bit of a brute force method. We had a lot of terms to collect. There were, in fact, 6 terms in total that we had, 6 cosines and sinusoids that we had to calculate. Another approach to solving this same problem is to do it graphically via the phasor diagram. So what we'll do is we'll sketch each of these phasors on the real imaginary plane, and then we'll draw them on top of each other to show their vector sum. And when you sketch your phasors on the real and imaginary plane, that's called a phasor diagram. And you can look at one of these diagrams and immediately know what the values are of each of your phasors. You can extract the phase information, the angle from the real axis, and the magnitude, that is the length of the vector, to construct B bar, C bar, and D bar. And in our problem, we want to find out what A is, which is equal to the sum of B plus C plus D. And so we can redraw this, again, on the real imaginary plane, showing the summation operation. And our final phasor, the value of A, is going to be connecting our origin to where our D phasor ends up. And so we can extract the phase angle and the magnitude of this vector to figure out what the phasor is. And so sometimes this can be a simple way to determine your vector sum, and sometimes it's not simple. So you have to look at the problem that you're considering and decide what approach to take, whether you want to do a brute force math method like we did up here, or if there's some kind of simplification that can be made by sketching it graphically. And to illustrate this, I've drawn 4 phasors on the real imaginary plane, and all the phasors have the same magnitude, and I've shown the relation for how the angles come off the real axis. So you can observe some symmetry here. You can see that our final phasor diagram is going to have consist of a single phasor exactly on the imaginary axis, because the angles are going to cancel out. So if we sum up all these vectors, we're going to get one final vector that points exactly along the imaginary axis. So this is an example of how a phasor diagram can allow you to quickly see what's going on and avoid you having to come up with, evaluate many different cosine and sine terms, as we would have had to have done if we were taking the brute force mathematical approach. The final benefit of the phasor diagrams is that it helps to build physical intuition about what is going on in your system. So that was our example of how to add up. All of this was under this bullet point here of how phasors can be a useful tool for adding periodic signals. Now I want to remark about how the phasor diagram rotates. So all of the phasors are multiplied by e to the j omega t to determine the final cosine value. So in this example that we were working on, all of our phasors had this form of our phasor quantity times e to the j omega t. And it was important that all the phasors had the same e to the j omega t, because that's what allowed us to pull the j to the omega t out on the left side. And so you can see from this expression over here that all of our phasors are actually going to be rotating as t advances in time, as time goes from 0 to some positive value. This whole quantity can be plotted on the real imaginary axis, and it will be seen to rotate. So when we take t as 0, we get a diagram like this phasor diagram up here, where we've got all of our phasors plotted. And then as we allow t to advance in time, the whole diagram is going to start to rotate in a circle counterclockwise. And so if we were to stand right here and observe the phasors as they tick past us, we can make comments about the relative angle of each, about when the phasor passes us as we stand there. And we can say, well, we're going to observe C before we're going to observe phasor B. So we'll say phasor C leads phasor B. And we know that when we go back to our original plot, we can see that up here because phi C is greater than phi B. We can also say that phasor B lags phasor C. And we can say that phasor D lags phasor B. And typically you'll say this with the context of some angle. So you'll say that phasor B lags phasor C by 10 degrees or 100 degrees or 2 pi by 2 radians. And you can quickly calculate that by subtracting your angles up here. So phi C minus phi B is how much phasor B lags phasor C. And the final point, which is probably obvious at this point, but is worth articulating, is that phasor diagrams allow us to quickly extract the mathematical expressions for our quantities, for our sinusoidal quantities. So I've sketched a phasor diagram for balanced three-phase currents. And we can easily convert this diagram to the sinusoidal expressions for these three-phase currents, because we've got on here the phase angle and the magnitude of the currents labeled. So this diagram is directly equivalent to saying the following. And so in these expressions, we had the magnitude of each phasor indicated on our diagram, and we had the angle of each phasor indicated on our diagram. The one piece of missing information is what the frequency of the phasor is. So you have to know all the information that's labeled on the diagram right now, plus you need to know what the frequency of the diagram, has been drawn for. And oftentimes this is implied within the context of your problem. So if you're talking about line currents, you know that the frequency is going to be 60 hertz times 2 pi. However, in this class, we'll oftentimes be talking about phasor diagrams for different harmonics. So we could actually be talking about 2 pi times 60 hertz times 3, that'd be the third harmonic, or 2 pi times 60 hertz times 5, that'd be the fifth harmonic. And so sometimes we'll explicitly indicate what the frequency is that we're drawing our diagram for, and other times it'll be clear from the context. But the key piece of information on this is that in order to readily go between your mathematical expressions and your phasor diagrams, you need to know the magnitude of each phasor, the angle of each phasor, and then the frequency that that phasor is operating at. And again, this can be in the time domain like we've indicated here, or it could be an angular span like the inner bore of your surface of your stator going from 0 to 2 pi. So in summary, this video has reviewed the phasor representation of sinusoidal waveforms. We've talked about the very fundamentals from where phasors come from Euler's formula. And we've then talked about how we can use exponential mathematics to construct this into this useful phasor form, and how this is a useful tool for adding periodic signals, as well as two techniques for adding periodic signals: a brute force mathematical approach, where we again went back to Euler's formula, and a graphical solution via a phasor diagram. Finally, we concluded by talking about how these phasor diagrams rotate at a certain frequency, and how that this frequency is necessary so that we can easily convert between mathematical representations and the diagram.